We can go ahead and get started. Our last, I guess, sort of necessary topic, we've already been kind of playing around a little bit with this already without having it as a formal topic. It's also a pretty straightforward, maybe dry, kind of sort of boring topic, so we'll do the best we can with it. I think what can be nice is once we become sufficiently proficient at doing file input-output in C, it really allows you to start to abstract some things away in your programs. And I think hopefully you'll see that as early as your project. So for example, the Pac-Man team, you have these different level designs. And yes, you could go into your program and like hard code the levels where you have just a whole bunch of if statements that are determining whether you've hit a wall at this point or something or the other. Or you could write a file that kind of describes what the level details are, and then you're basically building a game engine based on that file. And that can be a very nice way to separate game logic from like level design. And for quite a few of the projects, that could be a very nice thing to have here. So nobody put it in their rubrics as a necessary feature, but I kind of understand that we haven't covered the topic yet. You may find, after a little bit of overhead of getting to like opening and reading and working with a file and learning how to do that properly, you're actually going to save yourself a lot of lines of code by kind of pre-doing some of the things ahead of time and not having to recalculate things or not having to build all sorts of spaghetti logic to do something that could have been described via a file ahead of time. Here's where we are in terms of our schedule. We're actually a little bit behind. That's why I put the MQ Charlie on there, and we're actually a week behind that, and that's okay. Projects will begin this week. Our demo day is that Monday of exam week, and I'll tell you more when we get closer to that point. It'll be a celebration of a successful semester. It's not meant to be a very stressful thing. So we're going to talk this week about reading and writing files, and I think there's an important separate topic of text versus binary files, and we will talk about what that means in proper context. It is a little bit of a dry topic, so we'll use it hopefully maybe to just kind of improve or bolster our existing C skill set, and maybe if we get really bored, we'll do Flappy Bird in class. We should be able to. I don't see why not. Let's not give up on that dream at least. Because where I think we may see some value is not in the file I/O, but maybe getting a little bit stronger in Curse's programming, because like 6 of the 8 projects are going to use that. And so just spending time in class doing more Curse's programming could be a worthwhile use of our time. So hold me to that. If we get to Friday and we're complete experts in file I/O, we can start a video game. Going kind of blind here. Part of the motivation, and this is just part of the motivation, is the way we've been doing data entry so far in our programs has been pretty limited. I want to get 1,000 integers for this program to test something with it, and I've either been having scanf, where a user has to type in all 1,000 integers, or we've been passing them via that argc, argvia via the command line, or we've just been generating random data. It's good to kind of prove initial proof of concept, but it's a pretty limiting way of entering data into a program. In practice, we have our program's logic, and it tends to be separate from the data that we're going to execute that logic upon. Standard C library gives us a relatively straightforward mechanism for reading and writing to files to capture data as either binary data or text data. We'll talk a little bit more about this maybe even on Wednesday, but there's an important distinction between the two. It is very similar to how we, I think, intuitively understand how to access files. You can have a relative path to a file. So I can just have a file name as myfile.txt, and the assumption there is that file is relative to where I'm currently executing my program. Or you can also specify so-called absolute file paths. If this was window, your absolute file path would look something like c:/me/myfile.txt, or maybe in a more Unixy style with forward slashes there. Little bit of an editorial point here. When I wrote this bullet point in this slide, I thought that was intuitively obvious, but I think modern computing is kind of moving away a little bit from that, right? In terms of presenting you with a file system and expecting you as the user to organize your files and to be aware of directories and subdirectories. And back in my day, everybody knew exactly what C: meant and what /home/username meant. And nowadays, by default, you open up Microsoft Word, and it doesn't want you to organize where you put that file. It just wants to put it arbitrarily in the cloud somewhere, and it wants you to search for that file to find it later. It doesn't want you to know necessarily where your files are. Not to mention, computing support on your tablet or phone along the way. The trend seems to be, at least in terms of how it's presented to you as a user of a computing system, to not be as super aware of the underlying file system and organization underneath the hood. It is still absolutely there. It has not gone away in any way, shape, or form. But maybe it gets hidden from us more than it used to, where I, as a undergraduate computer user, had to be very clear where I was putting my files, how I was organizing my folders, subfolders, subdirectories, so that I could find things when I needed to, because you couldn't even necessarily easily search your files, or it would be quite slow if you tried to search your files. Um, Maybe that's part of the value add of this course, and for some of you, maybe you don't need it at all, but for others, it is an important thing to learn, which is how to become just a little bit more adept, certainly on the Unixy side of thing that replit provides for us, how to become a little bit more adept of finding stuff, organizing stuff, just being a little bit more aware of where files are placed in a system and how we can access things available to us in a system. It still, I know, looks a little magical when I go into the shell and type a million things, but we're getting a little bit better at that, right? In terms of understanding, we have these utilities, they tend to operate on files, and we can do a lot of things via file I/O. And the standard C library provides us some relatively straightforward functions to also operate on those files. In fact, kind of underneath the hood, and not exposing this much as such up to this point in the semester, we've already really been doing file I/O all semester long. We have been using printf and scanf, and those are really just a special version of functions called fscanf and fprintf, with two special defined files associated with the C library: standard in, which is for reading user input, and standard out for providing user output. We will see a function called fprintf, which is exactly the same as printf, except we specify the file we want to print to. If we called fprintf and specified standard out as the name of the file we want to print to, we would have the same exact functionality of our existing printf. So we don't really think of printf and scanf as being associated with a file. That's kind of the Unix philosophy, and that was the quote at the bottom here from Linus Torvalds, that's the whole point. Everything in the Unix philosophy is everything is a file. The thought is all your devices, all your device drivers, all your networking type access, everything is a file. Once you become adept at reading and writing to files, you can do a lot of advanced programming things using those same capabilities. So getting good at fprintf and fscanf and printf and scanf actually allows you to do more advanced things that you may not have realized in at least the Linux view of the world, where everything can be kind of treated as a file. So C uses the so-called I/O stream model, So a file is just a stream, or another way to think about it is just a sequence of bytes. So consequences of that kind of model of I/O is you don't actually read an entire file at a given time. You don't have to have a variable that represents all the data in a given file at a point in time. Instead, you have a data type that's provided by the standard C library that's really there to keep track of a position within a file. So in our C library for doing file I/O, we'll be declaring these file stars, a pointer to a type of file. It's really a handle that's provided by the operating system that just kind of keeps track of what file do you have open and where are you in particular in that file. You can think of this as, if this is my file.txt, it is just a sequence of bytes, stream of bytes, and the data type, the variable we use to keep track of that, is that file pointer, and we're just kind of keeping track of the file position along the way. We don't actually have a variable that stores the entire contents of the file. We choose to read or write given a particular location within that file. We'll see the benefits of doing that. It makes the functions very straightforward to access the file. There's maybe some downside to that way of looking at things as well. But the most conventional approach is we start at the beginning of the file. We kind of work our way through, either reading or writing as we go along the way. The closest historical analogy is that to like an old VHS tape, if you don't know what that is, and that's okay, where it's just a sequence of ones and zeros, and we have a kind of a physical position of where we are within that tape. There's probably a better, more modern analogy than that, but that's a perfectly valid one. And that's the same way we kind of treat our file, that we have the file itself, is stored somewhere in the system, and it is stored somewhere physically in the system, right? You know, your file is going to be a physical thing, right? It's stored in magnetic storage, or it's stored in some solid state or some flash storage in your system. And then what we're accessing is really just the platter, right? The mechanism to determine where we are at a particular location within that file. So we have those special data types for accessing, which we use via pointer for historic reasons. So we declare a file, all caps also for historic reason, a file star, we call it my file, and the function we use to access it is called fopen, which we can guess stands for file open. You provide either an absolute path or a relative path to that file. For a lot of what we'll do, relative path makes enough sense. We're going to put the file in the same directory we're executing things. So we have that pointer to a variable type file. We have the name of the file, in this case, a relative path. And then there's a second argument, which we'll talk a little bit more about, which is the mode in which we are reading or executing that access to a file. It is also very good practice. This is a pointer that's being returned by this function to kind of check. To check if fopen fails, it's not going to print out a message saying file open failed. It's not going to give you an error message in that traditional sense. It'll just typically return null or zero to that pointer. And so it is usually best practice, and certainly if you don't want your programs to crash on you a lot, to check for that immediately after calling fopen. We call it fopen. We return the result to that my file pointer. We then immediately check whether the result was zero or not, or check where it was null or not. And in this case, you know, we print out a message ourselves. Problem opening file. You know, it depends on what you're doing, but oftentimes for the kind of programs we're writing, if we're not able to open the file we want to open, the program's not going to go well, right? Things aren't going to succeed in our program. We probably just exit at that point, you know, return 1 or something and say, well, if the file wasn't where we thought it was, it's unlikely the rest of the program is going to work for us. I mean, that's not always the case, right? It could be we check to see if a file exists, and then we do different things depending on whether or not that file already exists or not. For a lot of what we're doing, it's more of, okay, we check if the file exists because we want to read from that file. And if it doesn't exist, there's probably not a lot of success for us in that program. So we should check for that versus having our program crash. From like a more architecture or a physical computing layout perspective, a file is actually quite similar to our existing understanding of what happens in memory, right? Memory is also this physical thing, right? We talked a little bit about SRAM versus DRAM and the actual physical storage of ones and zeros using transistors corresponding to addresses in memory. That's still the model for memory with our pointers that we've become more familiar with. Files can be stored in all sorts of different locations, but the word file usually implies this block of ones and zeros that are going to be arranged according to some preset, pre-agreed upon format and stored usually somewhere else. Files can be stored in memory, but oftentimes when we talk about something as being a file, we're referring to these ones and zeros, not in memory, but ones and zeros stored on my SSD or on my old school hard drive or on some other type of flash storage, some so-called non-volatile storage. That distinction isn't necessarily that interesting to us today as programmers, but what that tends to mean is if I have memory in my system and I pull the plug, that's volatile, it's gone. Whatever these ones and zeros were, disappear, if not instantly, very quickly once I've pulled power from them and I'm not refreshing those values. That's volatile storage. Whereas our files in our system, at least traditionally, the implication is that they're put in non-volatile storage, meaning storage that keeps its ones and zeros even when there's no power provided to it any longer. So files serve a different purpose in that sense, right? Files are then to store things that are to be used across programs, right? I create one program to write a file. Tomorrow I create a program to read that same file. And in between the creation and reading of that file, those ones and zeros are still stored in that location in our system. It's not a free lunch. The trade-off here is the performance, the speed at which one can read from these is significantly slower than the speed at which one can read from those. We're talking several orders of magnitude, right? If it's going to take us, it really depends, but if it's going to take us 100 clock cycles in your CPU to read a variable from memory, just rough order estimate, it's going to take 100,000 cycles or 1,000,000 cycles to read that same variable as stored in a file. So a very common approach as the programmer, what we want to do is we read all the stuff we need from our file and then we put it into main memory. And that'll be our most common approach to working with files in C. Open the file, read what we need from that file, copy it into variables so that for all the extra work we want to do with that data, those ones and zeros, we're operating based out of variables, we're operating based out of main memory. And then only when we're done, only when we want to make sure we're committing some result back out, we're going to write something that we want to use tomorrow or a month from now or what have you, then only then do we write the value back to our file. Certainly that's important, and there's all sorts of strategies if we really care about the performance of our software. But just from a practical consideration, that is going to be our common flow of things. But otherwise, it's still just ones and zeros located a particular way in memory that we access via particular functions dedicated for that purpose. So that's why this is a dry topic in some sense, is there really isn't that much new there. Let's play around with it a little bit. Here is example 1. This is just file open example. We declare our pointer and it is a file star. We don't need a new header for it. It's part of the same exact part of the library as our printf and scanf, our standard IO library. We declare it. We then set it to be the result of an fopen call, file open, where we provide either an absolute or a relative path to that file. This starts to become a little bit system dependent, but for now I think it's sufficient to say, we've done a little bit of this, right? When we were opening images with our image library, but we weren't too focused on it. You can provide directories and subdirectories, but at least in this case, because there's nothing leading that double quoted file name here, it's all relative to where we're executing this program. So I'm saying fopen, file open, something in my directory /joe_file.txt. That's our first input. And the second input, and it's a string, it's not a single character, although it looks like a single character, is R in this case. Open it in read mode. We might be able to guess if we want to open file in write mode, what we would provide for that instead. A W, very good. Okay, and there's a couple other ones as well. It is very good practice to then pretty much immediately check after having opened the file whether we succeeded or not. It will return 0 if it was not able to open that file for all sorts of different reasons. Some sort of error message, a user error message, and then probably, at least like I mentioned, for the programs that we are writing this semester, it's probably going to be hard to recover from that. If you're expecting a file for your program to be successful and the file doesn't exist, for us, for the kind of things we are writing, we probably just get out of there, or at least be aware that we don't want to do anything else with that file pointer. It is null. If we try to read data using this file pointer, we'll be referencing invalid pointers. We're going to crash. Otherwise, we do whatever we want to do with that file. We haven't done anything yet here. And then only when we're done, only when we don't want to access that file any longer, there's the companion function called to fopen, which is just called fclose. I think by default, all your files get closed when your program exits anyway, but it's pretty good practice when you're done with the file, close that file. So in here, in our replit directory, I did just create a subdirectory. Inside it, I put a file called joefile.txt. It's a very nice file. There's nothing wrong with that file. We then execute this program, and it's able to find that file, and so it prints out successfully open file. If I instead change this to my directory, joefile2, we'll say .txt. Seems very unhappy. It says problem, it was just slow. Problem opening file, which is at least something, right? It's not crashing, but it's saying, hey, you should now be able to look back and say, despite my best intentions, file didn't exist. What did I, do wrong along the way? We talked a little bit about this earlier in the semester. In the Linux philosophy of working with files that we are doing here, these things, these dot, and then usually 3 characters afterwards, the so-called extension of the name of a file, they are meaningless for the most part in Linux. They are there for historical reasons. They also could be a nice hint to your users as to what you want that file to potentially have inside it. But this file being called .txt doesn't change a single thing about that file, at least in the Linux way of opening and working with files. We could call this joefile.jo, and there's nothing wrong with that. I just got to make sure I have such a file there. Copy command, so cd, go into that my directory, copy the file joefile.txt to joefile.jo, and it doesn't change anything about the program. It's the exact same program. It's just a meaningless thing. Whether Replit is smart enough to open arbitrarily named files, I hope it should be able to for the same reason. It's the exact same thing. It's just called something that maybe is a little bit more meaningful, a little bit less meaningful for us if we don't use kind of historically, conventional names for various types of files. Again, this is a relative directory. If we want to figure out the so-called absolute directory, well, it's a little bit harder in Replit because it's in this cloud environment. If I open it today, it may be a different directory name than when you open it tomorrow. But in general, in this shell tab, it does actually give you a version of the absolute directory name for where things are located. That ~/ is convention for going to my home directory, so it is still a little bit of a shortcut, but we can find the full name of it. So home directory, I don't know why it's complaining all this. Thank you, sir. That's now the absolute directory for that file, and it should, problem opening file, that's wonderful. It should be okay with opening that directory. Well, we can look at the actual name for what that expands out to. PWD is print working directory, and it gives you the actual full name for that directory. This could just be a copy paste error. It may not be anything meaningful. /home/runner. That implies that the user of this Linux environment is a user called runner. It has to do with some of the virtualization and cloud options. You can usually type in who is logged into this machine right now. Nobody. Usually you can be able to type in who am I? I am runner. So it gives you the name of the user you currently are on. This one should be successfully opened, so we can provide that absolute path. It really depends on what you want to do. The value of the relative path is I can choose to move this into a completely different top level directory, and then the subdirectory still has the same name. It should still work. There's downside as well. If I decided that, right, we have this executable, so ls shows me the contents of the current directory. Main is the name of the executable we're running. If I instead change my mind and want to move that main somewhere else, I want to move it into the temp directory. The program is the same. I haven't hit run. I haven't recompiled the program. But now when I type in main, it's going to tell me problem opening file, even though I didn't change the program at all. Let's copy instead of just move it. Let's move it back up a directory. When I'm in this directory and I run main, it's a problem. When I'm in this directory and I run main, it's successfully opened. So that's the downside of a relative path for our directories and our file names. They are relative to where you are currently executing your program. When I am in this top level directory, there is a subdirectory called my directory, and then there is a file at that directory. When I'm in that temp directory, there is no subdirectory relative to it. It's not going to be able to find that file. Anything that's valid from sort of the path syntax we've been using all semester for accessing files will work for this as well. So if I want to execute it out of, I don't mean to belabor the point too much. If I wanted to execute this out of temp and to go up a directory to look for my directory and then look for file, you can do that as well. Hey, go up a directory first, then look for my directory, then look for that particular file. Now it's going to fail from the main directory, but now it's going to work when I execute it from the temp directory. So, you have to be conscious, cognizant, aware of where your things are being stored. It's not the end of the world if, you just kind of assume that everything is relative, everything is in the top level directory. If you have 1,000 files, though, that's going to be very painful to kind of organize and keep track of. If you have certain audio assets and image assets and other assets, you probably want to structure it at least a little bit relative to where things are located in your directory structure. So that second input to fopen specifies the mode in which we're opening the file. So file name, That R means open file, in this case means ASCII read. This is something that actually, if you do some Googling for what file options, you'll maybe find things that actually are not quite correct or not really valid these days. You'll read a lot of documentation about this B flag, which implies that you're going to open the file in binary mode, and that doesn't actually do that in any meaningful sense. For the most part, at least in my experience with fopen, these are the 6 potential flags you would want to be interested in using. R for read, W for write, and A for append, meaning add to the end of a file. And then there's a couple of options that allow you to open a file for both reading and writing. Oftentimes, at least for the kind of programs we write in a class like this, we oftentimes just need a file for reading or writing at a given time. We don't often need it for both at the same exact time. But it is interesting if you want to see what happens if both a file already exists and what happens if a file does not exist. We already saw what happened when we're doing read mode when the file does not exist. When it was read and the file didn't exist, I said, well, there's nothing to read. It returned 0 for that pointer. We got problem opening file. However, when we want to write to a file and that file doesn't exist, that's okay from that semantics. So if we don't have the file that already exists, what'll happen is it'll create a new file with that name. We can play around with that very briefly here. There's a little bit more going on here, so we'll just play around with this example. If instead, so we're still let's get out of this temp direct. Let's get rid of temp. We don't need temp anymore. And let's remove this joe file.joe. Okay. We saw that when we tried to read from joe file2.txt, we got the error. It did not successfully execute, right? That was because we were doing so in read mode, and the table there tells you that, right? Read mode, if the file already exists, we're good to go. We'll read from the beginning of the file. But if the file doesn't already exist, we're going to get an error. We're going to get a failure to open. Write mode is a little different. Write mode, if the file already exists, it's actually going to blow away that file. So be a little careful when you do that. Don't open main.c in write mode from your programs. It happens. I mean, you know, we get kind of stuck with what we're trying to do when we accidentally open up the wrong file. You'll delete the contents of that particular file. But, and maybe ideally this was what we would want, if the file doesn't exist and we try to open a file name in write mode, it'll create that file. So if instead of R here we put W, there are still reasons it could fail. If you're trying to write something into a directory that you don't have access to, if it's invalid character names, or things, so it can still fail. But for the most part, you provided a valid file name, a valid path, and it's never going to fail. It's going to successfully open file. And what happened here, I don't know if you saw it, we did an fopen with that new joe file2.txt, and it created that file for us. It is blank, but it created that file for us. We can put some content in that file. Now, what happens when we run this again? We're going to call fopen on joe file2 with write mode enabled. Let's go back to our trusty table. Write mode, it's going to create a file for writing. If the file already exists, it's going to destroy the contents of that file. Successfully open file, and I guess I generated pretty quickly here, but it deleted all the contents of that file, right? That file is now empty again, which may or may not be what you want. Replit with the history feature, so you click here in that lower right-hand corner, does kind of okay with that, but it depends on whether you've logged out or not. It doesn't always keep the contents. It's actually keeping track of like my keystrokes along the way. But if I needed to, and I blew away a really important file, I could roll back one revision and restore to that version that had that oh so important text, in that particular file. Other way you can get in trouble with fwrite is if you accidentally, again, if I'm just typing it in, that would never happen, right? I wouldn't put garbage text there in the name of the file. But if it was a variable, right? If it was a car array, and that's going to be the name of the directory and file that we want to open, fopen, assuming you have permissions, is going to at least try to put things in those locations for you. In this case, that directory didn't already exist, but it also depends on the system whether it would give me permission to arbitrarily create new directories when I'm doing my fopen call there. Otherwise, once you've had your file open, so fopen, and later finished with fclose, everything that goes in between fopen and fclose is documented in that same exact manual, that same exact reference page that we've been using all semester. We've been able to hide from it for the most part with regards to, well, the basic printf and scanf works, let's not worry about anything else. But for the most part, these functions are exactly the same. So if I look for the documentation for fprintf on that page, it's exactly the same. It's actually not documentation for fprintf. It's the same exact documentation for the entire category of print functions. Same for the entire category of scan functions here. The main difference is what you are scanning along the way. The ones we use for the most part are just regular scanf, so read in from the user input. Now we're going to be using fscanf. It's kind of hard to tell in looking at it, but it's exactly the same as scanf. You are just passing in that file star that you've opened, and now you're reading things from the file. It's like there's someone typing it in, but it's already been typed into that file, and you're reading in that content here. The other one we haven't used that much, but actually can also be extremely powerful, and think about using this maybe even in your projects, is scanf, right? We're scanning f as if someone's typing something in, but the assumption is they've typed it into a string. And so we're kind of parsing that string and getting back out what we need from that string. For that choose your own adventure program in Lab 8, which is quite tricky, there's no doubt, scanf can actually get you quite far in that example. But otherwise, yes, it's written in this kind of formalized documentation style of things here. Otherwise, it's exactly the same. Once you have your file open, you can fscanf it or fprintf it, but it depends on whether you've opened it in read or in write mode. This example, just called it file write for the second example here, just showcasing a couple of those functions. The joke here is there's no shortcut. I could try to walk through every single one of these functions, and there's about 50 of them. You know, that you'd probably hate me, and I think I'd hate myself by the end of that. The ones you typically need to know, fprintf, fscanf, beyond open and close, right? Open, close, fprintf, fscanf can get you pretty far. fputString, fgetString can also be useful, but you can kind of get away without doing it. That lets you read basically a whole line from a file at a time, or write a whole line to a file at a time. That can be very useful. The syntax is a little bit different for whatever historical reasons. fscanf here reads in a single integer, stores it like we've been doing with scanf. fgets overwrites a string array, a buffer in your program, with up to 256 bytes read from my file. It'll end at a new line. So it'll read an entire line from a text file. fputs does the same exact opposite thing. Write 256 bytes from this array into the file. Those four get you pretty far with text processing. But there are other ones as well we sometimes use. There's a function that tells me am I currently at the end of my file. That can be very useful to know. I have a while loop that's processing all the elements in my file, and I need to have some way of knowing, am I done? Did I get to the end of the file or not? That is one way of doing it. We can also choose to explicitly rewind our tape. Be kind, rewind your tape, rewind your files before you return them to get us back to the very beginning of the file, and there's a function to do exactly that. Less commonly for the kind of stuff we are doing would be to specifically fast forward or rewind the tape to a very particular location based on a byte offset in the file. There could be some value in doing that, but for the most part, we can get away without doing both fseek and ftell. These four will get you very far, plus fopen, fclose. feof, we do use sometimes, and I'll show you a couple of instances of it. Oftentimes, you can use fscanf as your own feof. You can use fscanf, and if it didn't return anything, we're likely at the end of our file. So in this example, we're just showing just a couple of these things. So fopen, file is just called new file. Here, there's no extension for that file because, as I mentioned, at least in the Linux view of the world, extensions are kind of meaningless. So we could have called it new file.txt or new file.jo or new file, whatever. It doesn't really matter. It's whatever we put in there is what makes it a file of one way, shape, or form. Check, good practice, just like with our memory allocation, with our file opens, check if it succeeded or not. If it didn't, just get out of here. Something bad happened, the program's never gonna work anyway. Now, our fprintf calls look very similar, I think, to our printf calls. We just have that new input in the beginning, which is the file we're actually printing to. Because we could have a lot of different files open. You could have 100 different files open with 100 different file star pointers in your program, and you have to specify which file you actually want to update with that printf information here. It's exactly the same in terms of the rest of that function call to our regular printf. You can pass it a boring old string. You can also pass it a float. You can do all the format string specifiers that we've already been doing all semester long. Anything you can do with printf, you can do with fprintf. They are identical functions. The only difference is here we specify a particular file we're doing all that printing to. This is just to show proof of concept that, hey, we can open a file, we can write a bunch of stuff to it, then we can close it. If somewhere later on, later in our program, we want to then check what context we actually wrote to the file, after we've closed it, we can open it up again, confirm that it worked. So always kind of continue that. This example is using both feof and fgetS. When we're going to call fgetS, we generally need to know the maximum size of any given line in that file. That can be a little bit tricky. If you yourself wrote the file, you have that knowledge about how long a given line of text is in that file. But in the arbitrary case, you don't necessarily know. There may be some upper limits of that function defined, but you have to be a little bit careful for that. For any assignment I give you, for any program we work on, I'll tell you that 256 is enough, so you don't have to sweat the details. But in this case, we are hard coding it. We're not doing that dynamic memory allocation here. It won't work with dynamic memory allocation. Or if it would, you'd still have to specify the amount ahead of time anyway. A buffer array of 256, we're going to have a while loop that's going to continue until I've reached the end of my file. feof file, end of file is what that's checking. It returns 1 when true. So that's why we have kind of the inverse operation, the not operation there. You could also have said, while feof equals 0 would also have been fine, but this is a very conventional way of doing it. Continue until you've gotten to the end of the file, call fgetS, overwrite line buff with up to 256 bytes of data from that file. It'll stop when it reaches a new line. And then just to kind of confirm that we read something, we're going to print out read and then the string that we actually read here. The main reason for text processing you'd want to use fgetS versus fscanf is because when you read a string in fscanf, like a %s, it stops at a space, right? It stops at any white space. fgetS only stops when it reaches a new line. So if you want to read a whole sentence or a whole line of a book, like you choose your own adventure, fgetS works a lot better for that. You don't have to know how many words there are in the sentence. You just read the whole block of text at one given time. You execute it, and I guess you can also just manually inspect the file that got generated, and it did include all the content that we had specified there. And then the final debug printouts is just confirming, we did read exactly as what we would have read when we were printing things out via the printf mechanism. There's more to cover about this, but this is kind of sufficient really to get started with file I/O. I know you've probably already done a lot of the Zybooks reading with regards to this. We'll work on the difference between text files versus binary files. That'll be Wednesday. Maybe Friday we'll flap some birds around. Well, if I can figure out how to do it on my own. Let's leave things here for today. You'll get some feedback from me hopefully tonight with regards to your project proposals. And as you finish Lab 8, it's really time to get started. Don't put it off for a week. Get started in earnest as soon as you can so you can be successful on it. Okay, thank you.